In this video, we're going to examine torque equilibrium. This is also known as a second order or a second class equilibrium. And this is going to follow the same pattern that we saw when we looked at static equilibrium, where we looked at the forces in y with the forces in x. However, now we also have torque to deal with. These problems will appear very challenging at first, but once you get the general pattern of how to solve them, they can actually be quite straightforward. It's just setting up three equilibriums and substitution. They can be used to solve a number of problems, especially in things like architecture, building shelves into walls, building floating shelves, tons of different anything that needs to not move on a structure, hanging signs, hanging anything. Chandeliers and houses all require consideration of torque equilibrium. And so these problems, while looking really scary at first, are actually quite helpful. And they're going to follow this idea that we've got three different net forces. We've got F net in x, which I'm going to abbreviate as this guy, the sum of forces in x. We've got the sum of forces in y, and we have the sum of our rotational forces, which would be sum of torques. And all three of these, in order for this to be stationary, all three must be 0. And so what we can do is we can look through this problem and go, what are the different pieces of this? What are the different forces active here? Now, the first one is going to be this capital T stands for the force of tension. That's going to be the one that we're looking for. However, we're also going to have a force of gravity because this is a platform being held up by a string or a cable of some kind, and it's going to have a force of gravity trying to pull it down. That force of gravity is going to act right in the middle. It's always going to be right in the middle. We're not going to deal with anything that has a less than uniform distribution of mass, and so our force of gravity will always be in the center of the object. So we're going to have that. We're going to have that force of gravity. We're going to have that force of tension. And then we're going to have some forces over here where this is connected to the wall. So we could say that this is a hinge. It's connected on a hinge. And so it's going to have some force normal in the y and some force normal in the x to balance it out. And so let's write these up here. In the Fx, in the equilibrium of Fx, we are going to have the x portion of our tension plus the x portion of our force normal. Now, the force in y, we should be able to write that out as well. We're going to have the force of gravity, and we'll figure out, we'll worry about which direction these forces are going after we have them all written. We'll take that into account in a little bit. We're also going to have a force in y from that tension, so we're going to have our tension in y, and we're also going to have that force normal in y. And now for the torque, we're going to have three torques. We are going to have the torque due to the hinge at the wall, and we account for all of our torque. So that's going to be the torque, we'll call that torque normal. Plus, we'll have the torque of our force of gravity, so we'll say torque of gravity. And we'll have the torque of our tension line. Now, torques are where we start to get interesting. I'm going to use pink to look at torques. I need to pick a hinge point. Now, this might seem silly. It's like, well, wouldn't it just be this point right here? Isn't this my hinge? But it's not necessarily, because this whole thing is stationary. It is not currently rotating. And I could imagine if there was mechanical failure, maybe this cable snaps, and then yeah, there's going to be a net torque over here in this direction, and it's going to start to rotate from this point. However, this hinge could break off the wall, and then we're going to start to rotate down from this side. We're going to make that motion. Or maybe both break at once and the whole thing starts spinning, maybe with an axis of rotation right there. So technically speaking, if this were to start moving, that hinge point could be anywhere. That might sound like it makes it harder for us, but it actually makes it easier for us. Because if we know that the hinge point can be anywhere, we can choose any point for our relative hinge point. For that radius, remember that torque is going to be defined as the force times the radius sine theta. That's that lever arm. So we can choose a starting location for our lever arm wherever we want. We could technically pick a point way out here, and it would still work. The math would still work out. We would just have to be cognizant that this is our point of rotation. But that wouldn't be a very helpful point. When we're working with torque equilibriums, we want to pick a point that's going to make our problem easier. And so we always pick one of the points where we have a force. So I've got this force of tension right here, but that's going to be what I'm looking for. So I don't want to put my hinge point here. I've got my force of gravity, but I can easily figure out my force of gravity. I just take 9.8 times my 45 kilograms. So I don't want to put it there. But then I've got this hinge point where I've got these force normals. I don't even know what direction they're going in, and I don't know their values. So I'm going to put my hinge point right here, and you're going to see what that does for us in just a minute. With that being our hinge point, so remember that our overall length is 2 meters. Our gravity will be acting at exactly halfway. So our gravity, our force of gravity, will be at a radius of 1 meter. It'll always be perpendicular to the ground. And so since this we can assume is level, our angle on our gravity will be 90 degrees. So let's go ahead and break out these torques. That's the first thing I'm going to do. And then we're actually going to start to spread out these equations, and we're going to be able to solve this problem. Now the first thing I do is I replace my torque with the equation of torque. That's going to be my force normal times that lever arm. So that's r sine theta. And then I've got my force of gravity. I've got the same thing, r sine theta. And then I've got my tension line. And that's going to have an r and a sine theta as well. When I look at this, what are my r values going to be? Well, the r for this one right here, this value right here, that'll be my maximum length because my tension line connects all the way at the end. So that will be 2. This right here, well, that's going to be my midpoint, which 2 divided by 2 is 1. And then this point right here, we said that's where our hinge point is going to be for our calculations. So that means that this pink point right here where my force normals are acting, that's going to have an r of 0, which makes this whole term go to 0. So now I've eliminated an entire unknown, and that makes this a very solvable problem. So let's go ahead and break everything out over here. I'm going to start with my equilibrium in x. And now when I have these values in x, what I want to do is I want to make them their parent function. So to find the tension in x, I would take the total tension times the cosine theta. And I would do the same thing with my force normal. And those should both equal 0. So now I don't have any numbers here except for cosine theta. I don't know the theta for my force normal. So I'm going to go ahead and solve this problem for force normal. I'm going to want to find that later. So what I do there is I subtract force normal from both sides, and then I divide both sides by cosine theta. So I've solved my cosine theta for my force of tension, which is a known value because that theta is going to be 30 degrees. And so I have an equation here. If I were to find my force of tension or my theta, I could solve for my force normal. Now, if I'm not able to figure out the theta, that's okay, because what I'll be able to do later is solve for Fnx and Fny, and I could punch those numbers in. But that will come later. So let's go ahead and move over and solve for my forces in y. Now, just like before, I broke both of these out into their parent functions. And now, because gravity is a known quantity, I'm going to solve for that and I'm going to move it to the other side. Now, I've got a value of 441 for my gravitational force, but is this going to be a positive 441? Now this is going to be a negative 441 because that's going to be pointing down. So when I move this to the other side, I'm actually going to be adding 441. So I'm going to have a positive 441 equals my Fn sine theta plus my torque times the sine of 30. The sine of 30 will be 0.5, so let's just put that in right away. We have one less unknown to deal with. And then let's solve for our torques. So now when I've got my torques all set up, because I was able to drop out that force normal value by putting my hinge point there, I'm able to solve for my force of gravity, and I can simplify this expression here. And then I would only have one unknown. So I can actually figure out my force of tension just for my torques. But let's take a gander at this. This 441, is this going to be positive or negative? How would I know? Well, this is going to be pretty contextual because I made my hinge point this point right here. So that means this is going to be my point of rotation. Now, when we look at torques, anything I have going in the clockwise direction, that will be negative. Anything going in the counterclockwise direction will be positive. So now on this side of that hinge, anything going up will be positive, anything going down will be negative. And so I can see that my force of gravity here, that'll be going down from this side of the hinge point, so that'll be going to the negative. So that means that that force of gravity, that torque of gravity, will be a negative number. So I need to put a negative here. So it'll be negative, and then 441 times 1, well, that'll be 441. Sine of 90 is 1. So my torque due to gravity is also negative 441. And then my torque is going to be multiplied by that radius of 2 meters times the sine of 30, which the sine of 30 is 0.5. 0.5 times 2 is 1, leaving me with torque. And you might be a step ahead of me here, and you might see that if I add 441 to both sides, I get 441 equals my torque. So now I have the value of torque. Now I can come back in to these equations and solve for my force normal. And let's go ahead and do that. And so when I multiply these together, I get 220.5. I'm going to subtract that from both sides, leaving me with 220.5 equals Fn sine theta. Now notice here, I've got force normals and my sines right here. How can I solve this equation? Well, there is a trigonometric identity that we can take advantage of. This is going to be one that will not come up very often, but it is really useful to know. And that's going to be that the sine of theta divided by the cosine of theta will equal the tangent of theta. So if I get my sine divided by my cosine, I can get my tangent here. And then I would actually be able to solve for this theta right here. So let's go ahead and do that. Let's plug one of our equations into the other in such a way that I get sine divided by cosine. Now that shouldn't actually be too hard because this equation up here, I can see that that's going to be Fn, negative Fn, times 0.866 times 441, leaving me with 380, and then I'll round to 382 divided by cosine theta equals Fn. And notice this had a negative up here, so let's move that to the other side by multiplying both sides by -1 to make this negative. So then I can insert this in for this guy right here. And when I do that, I'm going to move this down here, I get 220.5 equals negative 382 times sine theta over cosine theta, leaving me with 220.5 being equal to negative 382 times tangent of theta. And now I can divide both sides by negative 382. So I can do this. I can set it up like this. And I can solve for that angle. And I get an angle of negative and I'll just round to 30, negative 30 degrees. Convenient. So if I move this over here, if I look back at my drawing, negative 30 degrees, when I solve for that tangent, that means negative 30 degrees be out here. So my force normal is really up in this direction because I'm going from the left, and that's going to be 180 going down from there. Negative 30 is going to go down from 180. So there's my angle, and now I can plug that negative 30 degrees, I can plug that in right here, and I can get my force normal. It's going to take negative 382 divided by the cosine of 30. That'll get me negative 441. So my force normal is actually 441. That's pretty interesting. We get 441 for all three of our objects. So we get this nice force equilibrium. I get this equilibrium of my tension being 441, pulling in this direction. My force normal would be 441, really pulling in this direction, with my Fx pushing to the right and my Fy pushing up. That's balancing out the force of gravity right here. Fantastic. Let's do another one.